So I recorded the video for section 6.9 a few months ago, and I finally got around to watching my video. Each of the problems in this section is a word problem, and each of the problems you get a lot of decimals in the word problems, and all the answers that I can remember are decimals. And usually when a problem's going to have a decimal answer, I think ahead and tell you in the instructions of how many decimal places that I want you to round to. In this section, I don't tell you how many decimal places to round to, which is really not good practice for me. So because I didn't say what to round to, feel free to write all your answers as 2 decimal roundings. That would be completely fine for me. When you go through the video, because there aren't instructions that tell me to round to 2 decimal places, sometimes I round to 2 decimal places, other times I round to 3 decimal places. I might have even done 1 or 0 decimal places in one of the problems. So I'm really inconsistent, and it bugged me when I watched the video that I was inconsistent, but I didn't really feel like re-recording the whole video. I don't think it's going to take away from you understanding the material, my inconsistency in my rounding. So if it doesn't bug you, feel free to round every answer to 2 decimal places. This means that when you're going to check your work, if you're going to check your answers or look at my solutions manual, there's a chance that your answer won't match up perfectly with mine because my rounding might be a little bit different, because the instructions didn't tell me to round to 2 decimal places. I might have not rounded to 2 decimal places. So just bear with me as you go through this section, and if you don't let it throw you that I may have rounded differently than I'm telling you to round. So just round everything to 2 decimal places and you'll be completely fine for this section. In section 6.9, each of the problems is a word problem that gives us a bit of data. What we're going to do is we're going to graph the data. We're going to look at the graph to figure out what kind of function would best model the data, and then we're going to find an equation of a function to model the data and then use that to answer questions. The data in this section will follow kind of one of 3 different styles of graphs, and based on what the graph of the data, the shape of the graph of the data looks like, it will tell us what kind of equation to fit the data. And real quickly, the 3 types of equations that we might use to fit data in this section, or make our data might look like, the 3 types of equations that might be appropriate are equations that represent exponential growth, equations that represent exponential decay. I can't spell exponential. And equations that model logarithmic growth. Logarithmic growth. The classic exponential growth equation that we've been looking at so far is in the form P of t equals P sub 0 times e to the kt power, where k is some positive number. This is an exponential growth function. Let me just show you, using a real simple exponential growth function, what the graph of an exponential growth function looks like by just making up a simple function like P of t equals 3 times e to the 0.4t. This would be an exponential growth equation. It has a number in front of an e, and usually a positive exponent and a positive decimal and an exponent followed by a t. Let me go ahead and graph this on my calculator really quickly just to show you the shape of an exponential growth function. So I'm going to put y equals 3 times secant and ln to the 0.4x, and let me do zoom standard. The graph of an exponential growth equation will look something like this. It just kind of goes up and to the right, kind of like that. And the bigger the exponent, the steeper the graph. If this exponent 0.4 was like a 0.2, when I graph it, it'll be less steep. But the graph just kind of meanders up and to the right. So data that follows this sort of pattern we'll call exponential growth. Exponential decay is basically the same formula as exponential growth. except the k is negative, and that will make the function kind of decrease in some sense. This is your classic exponential decay function, and an example of an exponential decay function might be something like p of t equals to 2 times e to the negative 0.25 t. Let me just graph that just so that we know what an exponential decay function looks like. So I'm going to graph the function y equals 2 second ln negative 0.25 x. And when I graph this with my standard window, I kind of get the opposite version. It looks something like this. Data that follows this kind of path, we'll say follows an exponential decay path. And the last kind of function that we might use is logarithmic growth. And I think the equation for logarithmic growth, oh gosh, let me make sure. Let me peek at my calculator pretty quickly here. Is I think it's going to be something like this: a plus b times the ln of t. I think that's exactly how it's going to look. I'm trying to remember what my calculator produces for logarithmic growth. It might use slightly different letters. This will be an example of logarithmic growth. P of t equal to maybe 2 plus 3 times the ln of t, or x. Let me graph this for you just to give you an idea of a shape of a logarithmic growth function. So 2 plus 3 times the natural log of x. When I graph this, the data looks something like, the graph looks something like that. So these are the three kinds of shapes that I need to be aware of. In this section, we're going to be given data, we're going to plot the data, and then we're going to compare the plots to each one of these shapes. And the shape that the data most closely relates to is the kind of regression that we're going to do. My calculator does a really nice job on logarithmic regression. It doesn't do such a nice job on exponential regression, specifically because when it does exponential regression, it doesn't put it in the form that we want the regression to be put in. It gives me a correct equation, but in a kind of an awkward form. And in order, when we get into the algebra, in order to take my calculator's equation that it generates and put it into a form that's useful, I need to know this formula, that e to the ln of x equals to x. This means that any number, like e to the ln of 3, will equal to 3. If on my calculator I entered second ln e to the ln of 3, that's going to equal to 3. Or similarly, this would mean that 7 equals e to the ln of 7. Like if I did second e and then to the ln of 7, it'd come back to be 7. So any number is equal to e to the ln of that number. That seems like it's completely awkward and out of place, but we're going to need this rule in order, when we do the regression on our calculator, if we do exponential growth or exponential decay regression, we're going to need that rule to take the answer that my calculator gives us and put it into a form that is one of the standard forms for exponential growth or decay. So let me just start by doing problem 1 as opposed to doing my problem 2. And I'll skip problem 2 and not do it. I'll do problem 1 in place of problem 2. So problem 1 gives me some data, and the data gives me the temperature of coffee after it's poured from a pot into a cup. Basically says each one of these numbers in the top column, top row, is a time, and each number in the bottom row is a temperature. So at 0 minutes, the coffee is 179.5 degrees Fahrenheit. At 15 minutes of just sitting outside in this coffee cup, it's down to 141.7 degrees Fahrenheit. At 30 minutes, it's at 120 degrees Fahrenheit. So each of this table represents points of the form time in minutes and temperature of the coffee. The first thing I want to do in part A is to plot the data using my graphing calculator. That means I need to plot points. The first point I'm going to plot is 0 for the x and 179.5 for the y, which would mean at 0 minutes the temperature is 179.5 degrees. The second point I'm going to plot is at 5 minutes the coffee is 164 degrees. In order to plot points on my calculator to get my graphs to happen, I need to do a stat plot. So now I'm going to enter the data on my calculator. What I'm going to do is in list 1, I'm going to get all the x values like 0, 5, 8, all the way down through 34. And in list 2 on my calculator, I'm going to get the temperatures like 179.5, 164, 154, all the way down to 118.5. And we have to remember how to enter the data. To enter the data on your calculator, first you hit the stat button, and then after I hit the stat button, my calculator naturally has the edit highlighted. Once I hit the stat button and my calculator has edit highlighted, I hit enter, and I should be able to see list 1 and list 2. I think I've just entered this data because I kind of messed up the first time I recorded this video. And I want to enter all the x's in list 1, all the y's in list 2. To clear out my data, I can just delete each piece of data by hitting the delete key. Or I could go up to the top of a list, hit the clear followed by the enter. So you'll get to your screen where you see the list 1 and list 2, and in list 1 put all the times in minutes, and then go over to list 2 and enter all the temperatures in degrees Fahrenheit. The weird thing is, I can, on my calculator, I can use 2 fingers to enter data. On my phone, when I text, I can't. And I entered something wrong here because my lists have different sizes, so I'm either enter the number twice or miss the number. Let me try to figure out if I have everything in right. So 0, 179.5, 5, 164, 8, 154, 11, 149.2, 15, 141.7, I missed the 18 here, so I need 18, 134.6, 22, 125.4, 25, 123.5, 30, 120, and 34, 118.5. So I have the data in. To get my calculator to graph it, that's all I want to do now is plot the data. Let me get my calculator ready to plot the data. First of all, let me clear out the function that's in there and y equals and clear that out. My stat plot is on. Your stat plot might not be on. I can tell my calculator is ready to plot data because it has a plot 1 highlighted in black. To get that highlighted, if you don't have it highlighted, you hit the second button, then the y equals key. You hit enter when it has stat plot, and the first one probably says off if you don't see the stat plot. When you hit enter, if your stat plot wasn't on, you'd hit second and stat plot, you'd hit enter, and the cursor would start blinking on the on and you'd hit enter. Now the cursor up here says on and my stat plot's going to be highlighted. Once I get my stat plot on, to graph the data, I just hit the zoom button and I go down to option 9 that says stat and I hit enter. Now I look at that data. The data graphs something like that, and I look at the functions that I graphed earlier, and if I compare the data to the functions that I graphed, this most certainly looks like exponential decay. It doesn't look like exponential growth, and it doesn't look like a logarithmic function. Of the 3 functions I graphed, this function looks like exponential decay. So that's going to be important because when I go to model the data and make predictions from the data, I need to know what kind of data, what kind of equation would be appropriate. So I have my data in, done with that part. Now I'm going to say for part A, for plotting the data, I'm just going to say see my calculator. I'm not going to graph anything by hand. That's a waste of time. Decide the type of the regression model. I've decided that this is exponential decay. Which means when I try to find an appropriate regression model, part C wants me to find an equation to plot the data. My equation should be of the form, it should have a number in front of an e, and it should have a negative exponent followed by some decimal followed by the letter t. This is where my calculator fails me. when I know that I need to come up with an exponential decay function, my calculator doesn't do so well here. So how am I going to get my calculator to give me a function that it calls an exponential decay function, and then how will I transform that into the right kind of function? On my calculator, to get an exponential decay function is easy. You hit the stat button. So now I'm in the process of figuring out part C. I'm going to come up with an equation in the right form to fit the data. So I hit my stat button and I go over to calc, and I'm going to arrow down to exponential regression. My calculator doesn't have a separate function for exponential growth and exponential decay. I'll force my calculator to work for me, but it doesn't naturally work kind of how I want it to work. So I went down to exponential regression, and now I'm going to hit enter. And when I hit enter, after I have the exponential regression highlighted, I'm going to have my calculator know that the x's are in list 1, know that the y's are in list 2, and know I want to graph the function in y1. So I'm going to get my calculator on the main screen after I hit enter and see the exponential regression to have list 1, list 2, and y1 with a couple commas between them after the exponential regression. To get the list 1, I hit second and the number 1. Then I type a comma. To get list 2 or L2, I hit second and L2. Then I type a comma. To get y1, I hit the vars button. After I hit the vars button, I arrow over to yvars. When yvars and function are highlighted, I hit enter twice. Enter to get the y1 highlighted, enter to get the y1 on the main screen. Now my calculator is going to find a regression model for this data. It's not going to be the best, but it's going to be something I could transform into the best answer. When I hit enter next time, it tells me that the exponential regression model is in the form y equals a times bx times b to the x power, and I'm going to round to maybe 2 decimals. It says a is 172.54, b is I'm going to round that to 0.99, and it tells me what the r and the r squared is. Just like with lines, if r is bigger than 0.8, we'll think this is a good fit. Since the r absolute value-wise here is 0.98, it's a good fit. I don't need to really write the r down at this stage. What I need to do is understand the equation that my calculator gave me and figure out how to transform it into an equation with an e. Exponential growth and exponential regression functions generally have e's, and they don't generally have what my calculator gives. So my calculator for an equation, it says my equation is going to be y equals a, which is 172.54, times b, I'm going to put the b in a parentheses rather than using a time sign, to the x power. So my calculator gives me this equation, but I want an equation of the form p of t equals p sub 0 times e to the negative kt. That's my exponential decay model that I want to have. Unfortunately, I don't have the e. The x isn't really slowing me down. I can really start to write this as this. P of t equals 172.54 times 0.99 to the t power. That's not the part that's going to slow me down at all. So I've got the t into the function. That I can do just kind of randomly. You can change any x to a t. I need to get an e in place of this 0.99. Super easy to get an e in place of the 0.9, because 0.99 equals e to the ln of 0.99. I'm going to use this formula, kind of like I used it here, and inside the parentheses where I have that 0.99, I'm going to replace the 0.99 with e to the ln of 0.99, because e to the ln of 0.99 is equal to 0.99. If I did second e to the ln of 0.99, that equals to 0.99. So I'm going to replace the 0.99 with e to the ln of 0.99, and that gets the e into the function. This is why I need this horrible rule. So I'm going to get p of t equals 172.54, and now I'm going to type e to the ln of 0.99. I'm going to write e to the ln of 0.99 to the t power. I have my e. I don't have a negative in the exponent next to the t. Easy enough to get that. I'm going to now take the ln of 0.99 and do that on my calculator really quickly. So this ln of 0.99, the exponent, I can change to negative 0.01 because ln of 0.99 equals negative 0.01. So the next thing I'm going to do is I'm going to replace this with negative 0.01 because the ln of 0.99 equals that. I'm leaving the e because I want the e in the problem. So this is going to give me p of t equals 172.54 times e to the negative 0.01 to the t power. To finish this up, I'm just going to multiply these exponents to clear the parentheses. When I multiply those exponents, I can drop the parentheses that the e has, and I'm going to get the answer that I need for the next part. The regression model that shows the exponential decay the way I need it to would be this. So the function that models this data is this function right here. That's going to be the answer to part 1c. It says find the appropriate regression model and put it in the proper form for exponential decay. So my answer, this is just right here. This is my answer for 1c. I don't know if that's the hard part, but it's kind of the hard part. So I plotted the data on my calculator. I decided it was exponential decay. I entered the data, got my calculator's regression model, did a little tweak to my calculator's regression model to get it in the right form. Now I'm done with I have the appropriate regression model. Now I just need to answer the question. And it turns out that this answer isn't going to be the best. This is the graph of the function compared to the data. And you'll see that eventually the function starts getting under the data. And when I use it to make predictions, it's not going to give me the best prediction, but nevertheless, it's going to be what I use. Because the function doesn't go completely with the data, when I use the function, the graph when I use the equation to make predictions, it's just going to give an estimate that maybe isn't the best estimate ever. So, last thing I need to do for this is part 1d. That's predict when the temperature will be 115 degrees. The temperature is what the symbol on the left-hand side of the equation looks like. So when I go to do part D, I'm going to change the left-hand side of the equation to the 115 degrees, and I'm going to solve for the time in minutes. So to do part D of number 1, into the equation, the left side is the temperature. I'm going to put 115 degrees in for the temperature, and I'm going to leave the right side just how it sits. And I need to solve this for t. If I solve this for t, t stands for the time in minutes that it takes the temperature, the coffee to get to that temperature. So to finish this problem up, I'm going to solve this equation for t. To do that, I'm going to divide both sides by 172.54. I'm going to live in the 2 decimal world here because I don't want really ugly numbers to have to enter. So on the left side, I'm going to divide 115 divided by 172.54. And I'm going to write 0.67 because that's what that rounds to. So now I have 0.67 on the left side. On the right side, I have e to the negative 0.01t. We've solved a bunch of problems like this. To solve this problem, I'm going to take the natural log of both sides. I'm going to leave the left side the natural log of 0.67. On the right side, I'm going to drag the exponent out front and make that 0.01t times the natural log of e. The natural log of e is equal to 1. So the right-hand side is really just going to be negative 0.01t times 1, or negative 0.01t. And to solve for t, I'm just going to divide both sides by negative 0.01. The right side's going to give me t. The left side I'm going to do on my calculator. I'm going to do the natural log of 0.67 divided by negative 0.01. And I'm going to round that to just 40 minutes. So my work gives me that at about 40 minutes, the coffee will be 115 degrees. And I don't know if that makes sense or not, but I can tell. So what my work says is that at 40 minutes, the temperature is going to be 115 degrees. And you can tell it cools down really fast at the beginning, then it slows down. And what I've done is I've kind of created another point in this table without actually having to measure the temperature. I'm using the equation to predict that. This feels like a reasonable breaking point for problem 1, and we're going to move on to the next problem. I guess I just won't do problem 2, and we'll just kind of go from here to finish up this section. So I need to get the data entered here for problem 4. So I'm just going to kind of do it a little more quickly than I did last time. Hopefully you can get the data in. If you want to just jump and try to do your problem 3, you likely can do problem 3 without my explanation if you understood my explanation well enough for problem 2. But if you don't, let me do this. So the table gives me the spread of a computer virus. In the list 1 column, or in the top row, should I say, it's the number of days after the virus was created and the number of computers that were infected with the virus. So let me go ahead and just enter this data into list 1 and list 2. I'm going to put the days in list 1 by hitting stat and then edit, and then I think I can just add to my list 1 because my lists are real similar to the last list. And because this list is longer than my other lists too, I don't have to delete the numbers. I can just type over the numbers if I care to. You could delete every number, then type all the numbers fresh. But because the list was longer, I just typed over. So I'm going to double check to make sure my data is right. So I see 110, 239, 382, 4163, 5312, and 6656. I already cleared out the old y that I had in there, but if you have a y1 or y2 or anything, you want to clear that out. And now I'm going to do zoom stat to plot the data. And that looks like exponential growth. Of the 4 functions that I sketched, that to me is definitely not a logarithmic function. That's exponential growth. So I'm going to use exponential regression. So for part A, I'm just going to say C calculator. And in this section, the regression models are either going to be logarithmic. I can't spell calculator. For part B, it's either going to be exponential or logarithmic regression. And to be logarithmic regression, it had to look something like that, which it didn't. So this is going to be exponential regression. And it doesn't matter if it's exponential growth or exponential decay. When I go to answer part 4B, if you just said exponential, that would be fine. I'm going to say exponential growth because it's getting higher as the graph is getting higher as it moves from left to right, as opposed to exponential decay where the graph is getting lower as it moves from left to right. Now I'm going to do part C, do the regression, by hitting the stat button, going over to calc, and I have to go way down to find exponential regression. Looks like it's option 10. I'm going to hit enter, and then second and 1 for L1, and then comma, and second and 2 for L2, and then comma, and then vars, y-vars, enter, enter. Now when I hit enter, it's going to give me the equation, and it's actually giving me the equation y equals a, which is 6.244 times b, which is 2.216 to the x power. That's not great because it's not in the nicest form that we can have. So I'm going to change that 2.216 to e to the 2.216 power. e to the ln of 2.216 power. Trying to squeeze all this in on one sheet, and that's just a bad idea. Not giving yourself a lot of room is really setting yourself up to make mistakes, always. So I'm going to change this to e to the ln of 2.216 to the x power. The x eventually I'm going to change to a t. The y I'm eventually going to change to a function notation. But real quickly, let me get that ln of 2.216 made into a decimal. And it's 0.79. I'm going to round that to 0.796. I started rounding to 3 decimals. If you round to 2 decimals, I'm completely okay with that. And generally, I don't ask anything from this section on the test, so it's not something that I'd be so worried about anyways. Now I'm going to multiply the exponents that apply to the e and get y equals 6.244 e to the 0.796 x. That's an adequate answer for part C of number 4. Of course, it doesn't really fit what the question asks for in notation. So I'm going to change my y notation to the p of t notation and my x to the t, and the k is this 0.796. So for my answer, I'm going to say p of t equals 6.244 times e to the 0.796 t. So done with the formula, and I'll move on to part D. And in part D, I need to predict when 1 million computers will have the virus. In order to do that, I need to plug 1 million in for the left-hand side. And as I look at the numbers here, these numbers are just physically 10 computers, 39 computers, 82 computers. It's not 82,000 computers or 39 million computers. So to find out when 1 million computers will have the virus, I'm going to physically put the number 1 million in for the left-hand side of the equation and do the algebra to solve for the number of days. It's probably not going to be that many days because the growth rate is like, that's 80% for a growth rate. So to solve this, we've done this algebra a few times. The first thing I'm going to do is divide both sides by 6.244. I'm going to continue to round to 3 decimals. Every time I round, I start to, mess up. My answer gets less and less accurate, but I'm okay with that. So I'm going to go 1 million divided by 6.244. And I'm going to write down, I'm going to write down 160,153.74, and I'm going to round that to 8 equals e to the 0.796 t. And then I'm going to take the natural log of both sides. On the left-hand side, I'm just going to leave the natural log there. On the right-hand side, I'm going to make the exponent a coefficient. So that 0.796t is going to be multiplied by the ln of e. And again, the ln of e is equal to 1. So this piece I can just kind of cancel out. And that would give me the ln of this big number equals 0.796t. I'm going to divide both sides by 0.796. On the left side, I'm going to use my calculator. On the right side, I'm going to have my answer. So for the left side, I just do the natural log of 160,153.748, close my parentheses, and then divide it by 0.796. And that gives me 15.055 days. I didn't do a good job in talking about the rounding for these problems, and so I'm just going to do that, 15.055 days. In this section, if you round it to 2 decimals, I could be completely content with that. As I check your homework, I'm not going to be that picky. So that's everything for problem 4. Your problem 3 is a real similar problem. Instead of having a virus spreading through computers, it kind of essentially has a virus going through a population of people. And so this table that is represented in problem 3 just talks about how many people have a particular virus or how many people are sick with a virus after a certain number of days. And you're going to answer essentially the same questions that I did for problem 2. 4 that I just did. Five is another exponential regression problem, because when I say find the appropriate regression model, I tell you what form to put it in. So you might be able to do 5 just as well. I'll go ahead and work through 6, which is just like 5. So for problem 6, a chemist has a 1,000 gram sample of a radioactive material. He records the amount of radioactive material present every week for 6 weeks and obtains the following data. So at the beginning, there's 1,000 grams of that material, and by 6 weeks, it's down to 783 grams because it's radioactive and it's decaying. So plot the data using your graphing calculator. Let me go ahead and do that. On the last problem, I didn't even graph the function that I put in y1. If I wanted to show you the graph, it's a really nice graph. Let me clear that function out. I really didn't need that function graphed, but it never can hurt to have it graphed. Now let me enter the data here. So stat and edit in the left-hand column 0, 1, 2, 3, 4, 5, and 6. And in the right-hand column 1,000, 960, 922, 885, 850, 815, and 783. And then zoom stat. That looks like a line to me. You could probably do an equation in linear regression, or equation of a line in linear regression to match the data just fine, because it certainly looks like it's a line. It doesn't have much of a bend in it at all, the data. So if you wanted to do linear regression, that would probably be a decent way to predict this. Usually when we're dealing with decay of elements, it's usually exponential decay. When I decide on the type of regression right here, I'm going to say exponential decay just because of the section that we're in. But it's going to turn out that the linear regression, at least for the first few days, is going to be a reasonable predictor. The further we get out, exponential decay, the graph will stabilize, and that's probably what's going to happen. Eventually, the amount of material, first of all, it's not going to go below 0, and the exponential function will keep it above the x-axis, which will keep it from going negative, whereas a line, it would just look at, like at some point, like I have negative amount of that material left. So exponential decay is probably a better function. So let me find the function now for part C. Easy enough to do that. To do that, I hit the stat button, I go over to calc, I go down to exponential regression, and then second and 1 for L1, comma, second and 2 for L2, comma, variables, y variables, enter, and enter. And it's going to give me an equation. It says y equals to 1,000, I'm going to round to 3 decimals, 0.156 times 0.960 to the x power. And again, I'm going to change this to something that has an e. I'm going to go e to the ln of 0.96, because 0.96 is equal to the e to the ln of 0.96. Now I'm going to find out what the ln of 0.96 is. It's negative because it's exponential decay. I'm going to rewrite this function as y equals 1,000.156 times e to the negative 0.04, and I'm going to round that 0 up to a 1, times x. I'm going to multiply these exponents and get y equals 1,000.156 times e to the negative 0.041x. I also need to change to function notation just because the problem asks for function notation. When I go to answer part C, I'm going to just say P of t equals to 1,000.156 times e to the negative 0.041 t. And that should be an adequate answer. I maybe could come up with better letters to represent the left-hand side, but t for time feels good on the right-hand side. Maybe I could do W of t, like for weight, but I'm good with this. Part D, predict when 500 grams will be left. And to do that, I'm just going to plug 500 in for the left-hand side and set it equal to the right-hand side. I'm going to divide both sides by 500, or by 1,000 actually, 1,000.156. And that's going to give me let me change my calculator into rounding mode, because I want to round to 3 decimals, and that's going to round. It's hard to round, so I'm going to go mode, float, go down to 3 to get my calculator rounding to 3 decimals. Now do that again. 500 divided by 1,000.156, and that gives me 0.5. So I get 0.500, which I'm going to say is 0.5, equals e to the negative 0.041 t. Then I'm going to take the ln of both sides. On the left-hand side, I have the ln of 0.5 equals 2. And then on the right-hand side, I'm going to make the exponent a coefficient. That ln of e part is equal to 1. So I can just kind of cross it out. And I'm going to divide both sides by negative 0.041. On the right-hand side, I'll get my answer for t, and on the left-hand side, I'll use my calculator to do the natural log of 0.5 divided by negative 0.041, and I get 16.906 for the t. And I'm going to say that many days, so it's going to take 16.906 days to get the 500 grams of the material. So my answer for part D is going to be 16.906 days. Alright, so 5 is just the duplicate of number 6 essentially, so give that a go if you haven't already. The last two problems we have are going to be logarithmic regression, and the nice thing about logarithmic regression is we don't have to worry about modifying the function that our calculator gives us. The calculator function is completely fine. Again, I didn't take the time to graph the data, but you'll see how well the regression line fit the data in problem 6. It goes almost exactly through the points. Let me just do number 7 and not do number 8. So this has to be data that I borrowed from the internet. So it says the data below shows the average growth rates of 12 weeping Higgin cherry trees planted in Washington, D.C. At the time of the planting, the trees were 1 year old and 6 feet high. So the 1 and 6 gives me the age of the tree and how tall they were. At 2 years, they're 9.5 feet tall. And then when they're young, they grow really fast, and then eventually their heights start to stable out, and eventually they stop growing. So let me plot this data real quickly. Before I plot the data, I'm going to clear out the function that I have in there. Now I'm going to plot the data because part A wants me to plot it using a graphing calculator. Whoa, now this 3 decimals doesn't look good. I'm going to go back to mode, go to float, and hit enter. Now when I hit stat and enter to hit the data, it looks better. So my x's are 1 through 10. And I'm just typing over the numbers rather than taking the time to clear the list, because the list is longer than the previous list. So I should double check to make sure I have each data point in properly. 1, 6, 2.95. I'm just glancing to make sure my data matches up the actual data, because if your data is input wrong, then you're going to be doomed. So done. Now I'm going to hit zoom stat. I have the data in. I might as well graph it now to see what it looks like. And when I zoom stat, that's a logarithmic function, because the exponential functions either kind of look like that, or they look like that. This looks like this. That's the logarithmic equation. So this right here, I'm going to do logarithmic regression. And on my calculator, to show you what the logarithmic regression is, so I can write down an answer to this part, we're going to call it LN regression, or logarithmic regression. So your answer for part B, my calculator does natural log regression. I could call this LOG regression, or logarithmic regression, which would be fine. Now I'm going to find the appropriate regression equation, and my calculator equation is fine. It doesn't need to be modified. So when I go to do part C, I hit stat, went over to calc, and found the LN regression, which is the regression that we need here. I'm going to hit enter, and then second and 1 for L1, comma, second and 2 for L2, comma, vars, y vars, function y1, hit enter, and this tells me the equation is, I'm going to give 3 decimals again, is y equals to 5.94, I'm going to round that 5 to a 6 for the A, plus B, which is 6.28, I'll round that to 6, times the natural log of x. And I probably can put it in function notation. So as I go to answer part 7C, maybe I'll do a better letter. I'm going to do H for height, T for the time. So the height with respect to the time is 5.946 plus 6.286. And then I'm going to write the ln of t and make the x equal to time. If you left this equation, it would be perfectly fine. The graph must be really nice because the r is such a big number close to 1. If I hit graph, we'll see how well my graph goes through the points. And it goes through the points remarkably well, so it's going to be a great predictor. Last thing I knew is predict when the trees are going to be 20 feet tall. I do that by taking the left-hand side of the equation and changing it to 20. So I'm just going to put 20 in for the left-hand side of the equation, and I'm going to leave the right-hand side equation alone. And it won't matter when you're doing the algebra if you use an x or a t for the variable. It's the answer I'm going to get is going to stand for the number of days that it's going to take for the trees to get 20 feet high. To do this is a pretty monstrous problem. First thing I'm going to do is minus 5.946 from each side. I'm going to get my calculator back into the 3 decimal mode. So mode 3. Now do 20 minus 5.946. That's going to give me 14.054 equals 6.286 times the natural log of t. The next thing I'm going to do is divide both sides by 6.286. The right side is easy because the 6.286 is canceled and you're left with the ln of t. The left side I'm going to do on my calculator by going 14.054 divided by 6.286. I'm going to get 2.236 on the left-hand side. And now I'm going to get this written in exponential form. So this is going to be 2.236 equals to, and to get it written in exponential form, I have to do the longhand of this, equals to the log base e of t. Ln and log base e are the same. Now I'm going to scratch out the log and create an equation that has an exponent. The equal sign is going to stay right where it's at. The e that's the base is going to stay where it's at when I change this to an exponential equation. The 2.236 is going to move to the right hand side. the t is going to move to the left-hand side. When the t moves to the left-hand side, it's on the same level as the e. When the 2.236 moves to the right-hand side, my answer is e equals 2 to the 2.36 power. I'm going to get a better number for that by going second in ln, 2.236, close out my parentheses. I'm going to get t equals 9.356 days. That's going to be my answer to part D of question 7. So it's going to take, it's not days, it's going to be years actually, isn't it? Duh. Because the time here for the trees is their height in feet after years. So my answer for part D is going to be, it will take 9.356 years for these cherry trees to get up to 20 feet. And this feels like a contradiction because I know at 10 years they're only 19.7 feet. So when I go to do algebra to answer a question, because the equation doesn't fit the data perfectly, sometimes my answers are wrong. You'll see that right at the end, the graph is starting to overestimate. The actual heights are these square boxes, and the graph is the estimate of the height. The graph is overestimating. So it's the answer that I got is the answer that the algebra gave me. But in reality, I know that it's going to take more than 10 years for the trees to get these parts to get to that height. So the algebra strategy is only an estimate, and it's not always the best estimate. So I'm done with this section. Not going to dig myself any deeper of a hole than I just did. Let me turn off the stat plot by going second stat plot, hitting enter on the stat plot, toggling over to off and hitting enter. Now when I hit the y equals button again, the stat plot's going to be off. I might as well clear this function out, and I'll do a zoom standard just to get my calculator window back to a normal looking window. Alright, so we just have to do the review for this chapter, and we are essentially done with all the new material.